All right. Good afternoon, everybody. Any questions? Questions about the homework or in general? No? It's due today, 1 minute before midnight. Okay. I also posted the first project. This is due 2 weeks from today. Okay. The projects, I hope you can do it in teams of 2. Please have a partner. However, each member of the team needs to submit their own copy to Blackboard. Okay, it can be the same copy, but everybody has to submit. Okay, if you don't submit and your partner submit, you are still in trouble. Okay. Any questions again? No? All right. Yes.
For the colorblindness question on the homework, are you just asking if blue and like the 2 colors will look the same for a person without a deficiency versus a person that does have a deficiency?
Yes. So if I don't have blue receptors, right, and I look at 2 colors that have blue receptors see as different, would I see them also as different, or would I confuse them?
Okay.
That's the question, right? So what am I missing in difference between colors because I don't have blue in my sensor?
Okay, so like what we both can see properly, or what?
So if a color is a mix of blue and something else,
Yep.
and I don't have blue receptors, I will see the something else.
Oh, okay.
Make sense?
Yep.
Okay. All right. How about problem 3? Nobody has questions about problem 3? Everybody always has questions about problem 3. You said it, yeah.
Yeah, I was just kind of confused exactly what it was asking.
See?
Yeah.
So before talking about problem 3, let me talk about problem 2. Is everybody clear with problem 2?
I think so.
All right. Problem 2. You have a room, right? And the floor of the room is made out of tiles. And the tiles have parallel sides to each other, not so crooked like I can draw, because I cannot draw on the board very well. But all of these lines are parallel. I have a camera looking at the floor, and the problem asks to show that these lines in the image look like they're converging, and to find the point where they converge. Okay? And pretty much everybody always with that problem, they can do it. Okay? Problem 3 is the reverse of this problem. Okay, problem 3, what I'm saying is I have a cube in 3D. Can you all see that cube there? Okay. That's being seen by a camera. And so what I have drawn over here is basically the picture of the cube. So it's a 2D picture of a 3D cube. And even though the cube has all its sides parallel to each other, well, three at a time, or 6, I'm seeing here things that do converge, right? Because again, the same problem, we have perspective distortion. Lines that are not parallel to the image plane will be imaged as convergent, okay? So this problem, what it gives you is the coordinates of where those lines converge. I forget what it was 10 something, I think. Okay, 10, 0, I think. Okay? So I give you the coordinates of this point. Now, in the problem 2 and the problem 1, what you saw is that the coordinates of this point depend only on the orientation of the lines. It does not depend on which of the parallel lines I'm talking about. Okay? So the problem what it's asking is give me the orientation of the parallel lines. So if you think of this in 3D, all of these lines are all parallel along some vector v in 3 dimensions. This is what I'm asking. Can you find that, given that you know that these lines appear to be intersecting here in the image? Okay? Yes?
So in problem 2, we have 2 coordinate systems. So we have to like transfer from word coordinate system to camera system.
So your would have to be, to be honest, I don't remember exactly how the problem is phrased, but the thing to remember is that when you apply the perspective projective equations that we saw in class, the points in 3D had to be expressed in the camera coordinate system. Okay? So if you take care of that and you apply the projection, you will find the projections of those points in the image plane, okay, where they need to be. Okay? Now, if to get there you first need to change the coordinate system, that's also okay. In other cases, sometimes what I have is to simplify the problem, I say the coordinate system and the camera coordinate system are at the same place. So you don't have to worry about that. Okay? Somebody did the job for you before. Okay? Did this clear your question?
Yeah, it makes more sense.
Okay. Yes?
There is another point the left direction. There are minus 10, 0.
Right. These,
Yeah, this is
for these lines, right? So this line, and this line, they're parallel to each other, right? And this line, and this line are parallel to each other. These two sets of lines are actually orthogonal to each other in 3D. Okay? So they do not converge on the same point. Okay? These 3 converge in one point, these 3 converge in another point.
yes. I mean the left point is unknown, or we already know that it is.
Yeah, this is minus 10, 0. Yeah. Okay. Yes?
So just to fully define the orientation of the cube, do we have to define both the vector going to 10, 0 and negative 10, 0? So that
No, well, yes. This vector v and this vector v. Okay?
right,
Yeah, I'm asking for those two.
those two vectors.
Yeah. Okay? Yes?
Yeah, I was talking about which means they are in a position to be 0.
Yes?
So we can get f from that.
Yes.
Okay, thanks.
Okay. All right. So the other announcement is that Gwen has requested that I announce again that her office hours are Mondays and Thursdays from 4:30 to 6, and they are in Dana 310. Okay, the 3rd floor of Dana. Okay. All right. So the plan for today is to continue talking about filtering, and so we will talk about noise cleaning, and also we will talk about edge detection. And what we're going to be doing today is all at very local level. It's a small neighborhood, usually 3 by 3. Okay. Next class, we will talk about more modern edge detection techniques that actually work at a much more global scale. So edges are not just any discontinuity in the image, but edges do mean something. They're the contours, the boundaries of some object. Okay, so they have semantic meaning. Okay, and we also talk about things like corners and other features. All right. Okay. So this is a wrap up of what we did on Tuesday. So we introduced the correlation operation, right? Which we said is a linear operator that what we do is we take a mask. A mask is just a small image. We call also sometimes a kernel. And we slide that mask over the image to replace every pixel in the original image with a new value. And that value is just simple, the sum of the products between the pixel values and the mask values. Okay? And so here's a expression that does that operation. The difference that this is not a convolution is that we have plus signs here. If I have a minus sign, that means I would be flipping things, and then I would be having a convolution. Now, in general, if the kernel, the mask, is symmetric, convolution, correlation, not difference. Okay? All right. Another way of more compact of writing the same things, a different way of doing it, a different notation, is just like this, again, sum of the products. Okay. And we saw an example of how we did that by sliding the mask over an image and computing values. Over here, the outer elements are being padded with zeros, so I have the answer of the correlation well defined everywhere on the image. But we discussed several ways that that can be done. Okay. Now, let's play a game. If I give you this image, and I do a correlation with this kernel, how does the image look like? The same, right? Why is that? Right. I'm just, when I put this neighborhood here, I'm just copying the guy that I am underneath. So it's basically the identity operator. Okay? How about if I do this? It's shifting, right? It's copying my neighbor where I was. Okay? And that's how it looks like. What if I do something like this? A what?
A low-pass filter.
Low-pass filter or high-pass filter? Why do you say it's a low-pass filter?
Because it's averaging.
This portion here, right? But it has a minus sign on it. Sort of. So this is a sharpening. So this guy over here, first of all, is boosting the center. It's making it higher. And then I'm subtracting an average of my neighbors. Okay? So I'm making myself more important with respect to my neighbors. Okay, so it is a sharpening filter that will accentuate my edges. Okay. All right. So we end up on Tuesday talking about noise, and I show you this example of the cameraman image, and I look at this patch over here, which is very rough if I zoom in on the pixel values, and I claim that that's probably due to noise, and that I really would like to have something more like this, smooth out. And so that gave me the beginning to actually start talking about probability, because for us, noise is going to be random. And so I went through some very short, brief review of probability, but right now, the things I want you to remember is, first of all, the mean of a set of random samples. We can estimate it by doing the average of the observations. And the standard deviation is given by this expression. And first of all, before I continue, why do I have here n minus 1? Anybody knows? Not n? Biasing, yes. So this actually makes that the estimate of the standard deviation in the limit will actually be the true standard deviation. So we typically do minus 1. Now, if we have many samples, n or n minus 1 will not do much of a difference. So sometimes we will drop the minus 1. Okay. All right. In this class, we're going to really be looking two types of distributions. One is a uniform distribution, and the PDF looks something like this. So outside this interval, the probability is 0. Inside the interval, every value is equally likely, right? And because the area underneath the curve has to be equal to 1, that means that the height of this box has to be 1 over the length of the interval. Okay? And the other one, of course, is the Gaussian, which is well characterized just by giving the mean and the standard deviation. Okay. Now, this is in one dimension. Many times we will be talking about Gaussians in multiple dimensions, especially 2 dimensions. Okay? All right, so let's talk about cleaning noise or smoothing filters. All right? So these are spatial filters, and today again we're going to be looking at 2 types of filters that can do the job. One is linear filters, and therefore that we're going to be implemented using a correlation or convolution. And then we will talk about nonlinear filters, which will be implemented using a median instead of a linear filter. Okay? But the idea is that we want to use these filters to reduce the noise, and the price that we pay is that our image will get blurred. Okay? Our edges will be less sharp after doing this. Okay? Especially if we're doing a linear filter. Okay? Blurring can also be used on purpose to close gaps. Okay? Suppose I have some artifact due to shadows, or my detection was not the greatest, and so I might have an unintended gap. And by blurring the edges, I might fill the gap together. So sometimes it's not a bad thing. Sometimes it's actually a good thing to have blurring. Okay? And as I said, we can do this by linear and nonlinear filter. Okay, so let's talk first about linear. Okay, and like he saw that box that was an average, and he said that has to be a low-pass filter. Yes, we are going to be doing this basically by doing an average. Okay, and what we're going to do is actually we're going to see that we can do an equally weighted average or a different weighted average, and both of them work, and they have explanations why I might want to use one or the other. Okay, as I said, they blur the edges. That means they reduce the sharp transitions between pixels. Okay. And they are, for those of you that have signal processing background, they're low-pass filters. Okay. All right. So let's look at the average filter. And the first thing that is that every element that I mask on that kernel has to be positive, and it will sum to 1. Okay. So really, it's an average. Okay. And if the elements of that mask, if the weights are all the same, we call that filter a box filter, right? Because when I plot it, it looks like a box. Every element in the kernel has the same height. Okay, so here is a 3x3 box filter. I could have a 5x5 or a 7x7 or 15x15, whatever. Okay, but what it has to be is that all the elements are the same, and the sum has to be equal to 1. So instead of having 1/9 in every pixel, what I did is I put all 1s and then 1/9 outside. Okay? But that's what it says, is that every pixel over here is equal to 1/9. Okay? So let's say if I look at this synthetic toy example, I have an image, and if you look at the numbers in this image, you see that in this region, the numbers are in the neighborhood of 9, 10, 11. Okay? And this upper corner here on the right is, on the other hand, much lower values, 0s and 1s and 2s. Okay? So there's a sharp change between this region and this corner. And the other thing that you would notice is that there is this guy over here, maybe hiding among the 9s and 10s, that is 99. So it's a much higher. Okay? All right. So my example here, what it wants to show is that, if this was clean, all these high values should be around 10. Okay? And these values around here should be either 1 or 2, I don't know, but it should be low. So what I have is an upper right corner that's very dark, and then the rest of the image is kind of bright. Okay? But because I have these noise variations, the numbers are not all the same. But I would like to have all of these numbers the same and all of these numbers of the same. Okay, so I'm going to run through this image, this 3x3 neighborhood averaging filter. And so again, what we're going to do is we're going to slide the mask over and do the sum of the products. And for this example, I'm not going to worry about the frame, the boundary. So, right now I'm shrinking my image. Okay, I could have add zeros outside or something else to do it, but it's easier to just shrink it. Okay, so when I place my mask over here, right, and I do the average of these numbers, you can verify yourself, but actually it ends being 10. So that means that this guy that was 10 remains being 10. Okay. Then I move the mask, and now let's say I put it here. Okay. And when I put it here, this is one of the low guys. Okay. But when I put the mask on top of it, half of the mask is in the dark area, and half of the mask is in the bright area. Right? Because it's one guy that's right at the boundary between the two regions. Right? And now what you see is that when I do the average of these 9 numbers, well, it's not going to be low between 1 and 2, because I have all these 10s and 11s also waiting in. Right? So the answer ends up being 4, okay? Which is low, but not as low as I probably would have liked. All right? So I keep doing that. I have a 1 over there. That's good. Okay? Let's see what happens when I put it in a 99. Okay. Again, in this region, I would have liked it to end up being something of the order of 10, right? But when I put it here, right, of course this guy is very high. So when I do the average, the sum of the products goes up, and the result goes down for 99, but not all the way down. So it ends up being 20. Okay. So the bottom line is that over here I'm doing a decent job of cleaning. Over here, more or less, but again, I have this problem where at the boundary, this guy became higher than what I wanted, and this guy became lower than I wanted, right? The 11 went down all the way to 7, because I have these 0s and 2s bringing him down. And this 1 went up, because I have these 10s and 11s bringing it up. So in the boundary, I'm not doing so well. Over here I did well, over here I did well. And over here I did a more or less decent job, meaning that I went from 99 to 20. Okay? Now, one problem that averaging has is that this guy over here, which was perfect, right? It was 10. It was the number I wanted. When I did the weighted average on that, the mask had a 99 underneath it. And so now that 99 is spilling over to the neighbor, right? Because it's contaminating my average and my neighbors. So now this guy that was actually perfect, well, it became 18. Okay? So we're seeing here 2 things that filtering with this average filter box filters have problems when I'm trying to clean noise, which are 2 things. One is, first, blur edges, right? Because now these numbers are bleeding into here, and these numbers are bleeding into there. And second, if I have a high spike, it also bleeds around. Yes?
We obtained 18 by just applying the mask to 10 there.
Yes.
But the 4 in the upper end,
Yeah.
the 1, yeah.
This?
That one.
Yes?
In order to obtain that one,
Yes.
We used 4.
We use these 9 numbers, right? So I have
When we use that, it doesn't equal to
1,
1.
2, 3, 4, plus 2, 6. 6 divided 9. And then
So you used 4 as a number for 1.
I think, okay, 6 over 9 is 1 over 3, so it's 0.33, and I then round it up to an integer. I'm rounding up things.
Rounding up.
Okay, I'm rounding up.
Okay.
Yeah, yeah. Yeah, like over here also 17, I went to 18, yeah.
So they are not related. We can apply the mask for every frame and then just calculate the numbers in each place.
Yeah, that
do it in a sequence.
No, that's the whole point. You always use the values before, okay? So yeah, I apply the mask. That's a very good point. I always apply the mask in the old values, and as I go, I am filling in the new values.
So because if you apply it continuously, it will get blurred and blurred even more.
No, yeah, no. So if I did one more filtering of this guy to trying to say, that 18, I didn't clean it up. Let's try to do another low-pass filter. I can try that, but it's going to blur more, and it's going to spread more. Okay? Yes?
In the output, what are the X's? Can you just
mean I don't care. I didn't compute it. I'm saying because my neighborhood is 3 by 3, so to put something here, I need to decide what to do on the outside. Okay, so for this example, I just didn't bother. Okay, basically I'm shrinking my image. Okay. All right, so now the question is, does this filter actually reduce the noise, and in what sense? Okay, so we saw, like, you know, in an intuitive way, yes, it was reducing variations, but at the same time also was doing bad things in other places. So can I say that this type of filter is actually reducing noise under some hypothesis of what the noise is about? How would you characterize that? Hint, this is where probability becomes handy. That's where I need it. Yes?
Decreasing the variance using the value.
Right. So what we're going to look at is what is the expected value of a pixel in my given image before and after I apply the filter. And I'm going to look at the variance of the noise. And if I reduce the variance of the noise, then I'm going to say I did a decent job. Okay? So let's start with my model. Okay? So to do that, I'm going to assume that my noise model is what we say is an additive noise model. What does that mean? It means that the pixel that I observe is equal to some ideal value that I would like to recover, the noiseless value, plus some noise. Okay? And so this is this little I means pixel I. Okay? So I'm just numbering my pixels. I'm looking at a neighborhood of size m by n, okay, which is the size of my filter. Okay? So again, every pixel in that neighborhood has a noiseless value, and then it was corrupted by adding to it some noise, which I want to try to eliminate as much as I can. Okay? So the output after applying the filter is going to be the sum of the products, right? That is the average of the values in that neighborhood. So I'm summing over all pixels in the neighborhood, so from 1 to m times n, and I'm summing the values I'm given, and then divided by the number of elements I have in the mask. So this is going to be the output at the center of that neighborhood, right? So I have a neighborhood, I apply the filter in that neighborhood, and now I have one value coming out. That's O. And now what I'm going to ask questions is about what is the expected value of O, and what is the variance of O. Okay? It's in a probability sense. All right? So what is the expected value of O? Well, I need to make some assumptions about my noise. Okay? So first of all, I'm going to assume that my noise is zero mean. Okay? That means that it's not making my images darker or brighter, right? In average, I add 0. Sometimes I add something that's positive, sometimes I add something that's negative, but in average, go to 0. Okay? So I'm going to assume that the expected value of the noise is 0 everywhere. The other thing I'm going to need to assume, not for my first question, but for the questions that are coming after this, is that I'm going to assume that the noise is uncorrelated to the value of the pixel and to the value of the noise in my neighbors. Okay, so I have uncorrelated noise. Okay, and let's assume I know the standard deviation of the noise. Okay, so I know that the noise has a standard deviation of sigma. Okay, all right. So now let's ask the question again. What is the expected value of the output at this neighborhood given this hypothesis? Bless you.
I had.
I had. Why?
The mean
Right, so I have here a sum of two things. This actually is deterministic. I'm assuming it's the true value. It's not a random thing right now. So the expected value of that is itself. This guy has expected value 0. I can sum up the expected values, right? And so in the end, I will have that the overall output will be actually the average of the I hats in my neighborhood. Okay. Now, if the neighborhood happened to be ideally constant, that is, if I didn't have noise, all 9 pixels should be the same, right? Then I will have I hat. If not, I have the average of whatever is in that neighborhood. Everybody with me? Which is a desirable thing, right? That means that after I apply the filter, the expected value at a pixel is basically the same thing as it was if I didn't have noise. Okay, again, assuming that I have a constant neighborhood. Okay, all right. So that's taken care. Now let's talk about the variance, okay, or the standard deviation. Okay. So this is what we just did, the expected of the output value. Now let's look at the variance. Okay, so let's look at the variance in the neighborhood before applying the filter. Right? I'm going to look at that neighborhood that is ideal plus noise, and I'm going to estimate the variance, granted for very few samples, right? I will have maybe 9 samples or 49 samples, depending on the size of the filter. But so what I have here is the definition again of variance. So I have the expected value of the square of the difference between the pixel value and its expected value. Okay. So now replace I by our model, which is I hat plus noise. And for the expected value of I have I hat, right? Because the noise has expected value 0. Square that and expected value of that. So if we expand this, right, well, this guy cancels with this guy. So what I have is the expected value of the noise square, right? And we say that in our model, we're going to assume that for every pixel, doesn't matter which pixel it is, it's the same, and it is sigma square. Okay? So this is before applying the filter. I have additive noise, 0 mean, uncorrelated, with the standard deviation sigma. And before applying the filter, that's how the variance of that neighborhood is. Okay. Now, let's apply the filter and compute the variance after applying the filter. Okay. So now I have the expected value of the square of the difference between the output and its expected value. Okay. All right. So again, replacing. The output is the sum of the elements on the neighborhood divided by the number, right? So this is the additive noise model. The expected value of O, we saw that it was the average of the neighborhood, so we square that up, okay? And when we span this square, what we end up having is that I only have these sums of ni squares, okay? And I'm claiming that this thing is equal to mn sigma square. Why is that? Why can I say that the expected value of this sum of noise square is equal to mn sigma square? Say it.
Is it the sample variance?
So I got sum of, I was using capital letters, n1, and so I square, right, which is n1 plus n2 plus n9 square. And I need the expected value of this. Okay? Here I use 9 as Mn, that is m equal 3, n equal 3. Okay? So how do I find the expected value of this?
The lowest is different because of this independent.
Right. So I could expand this expression, right? So I have a square, and so we have something that looks like expected value of n1 squared plus n2 squared plus n9 squared plus 2 times n1 and 2, 2 times n1 and 3, and all the cross terms. Okay? And again, I have now the expected value of a sum. So that's the sum of expected values. The expected value of this guy is sigma squared. And this guy, sigma squared. And this guy, and how many of these I have? Mn. Okay? Now, how about these terms? He said something about independence. How does independence help? Why is 0?
We can write as a multiplication of expectation and
Right. If they're independent, I can't multiply the expectations of each of them. And the expectation of each of them is 0. Right? Notice that over here, I don't do that, right? I don't do expectation of n1 times expectation of n1. Why not? Because n1 is as not independent from n1 as it can be, right? It's exactly the same, right? So I cannot just say this is 0. This is actually sigma squared, okay? But these ones, I'm assuming that there is no talk between the noise in one pixel and the noise in another pixel. And so each of them has expectation 0. The product has expectation 0, okay? So this thing nicely goes away, right? And so this becomes Mn sigma squared, right? And if you look now at the expression I had before, right? I had one Mn squared outside, so one of these guys cancels this guy, and now I have sigma squared over Mn. Okay? And why is this good? This is good news. Why is it good news?
Because your variance is less.
Right, I reduce the variance by a factor of Mn. Okay? All right, so if things I wanted them to be constant, they're going to be closer to constant. They're going to be closer to the mean value of the neighborhood. Okay, so that's good news. That means that our averaging filter, which is a very easy filter to implement, does reduce the variance of the noise. Okay. Now, based on this, how big should be my filter? How big should be the mask? How do I pick M and N? So last slide said that I reduce the variance by a factor of Mn. Yes, sir?
I mean, it seems like if you make the product Mn as large as possible, then
it would be a good thing, right? So I will reduce the variance. So that will say larger, 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 right? Why that might not be such a great idea?
blur out everything.
It will blur out, right? Because the larger it is, the more likely is that my neighborhood will be crossing boundaries. And when it crosses boundaries, it's going to start blurring things. Okay? So there is a trade-off. And that trade-off typically has to do with the scale of my image. Right? If things are big, I can afford to have a bigger neighborhood because I will not be crossing so much, right? And even, there is some limit to it. If it's big enough, I will always blur stuff. Okay. It's also not only the blurring of the edges, but also that 99 bad apple I had, it will spread even farther, right? So that's not good. Yes?
I don't get the point of like blurring in the image.
I'm sorry?
I don't get the point of blurring an image to reduce the noise, because then you won't see it.
So,
Blurring the image.
well, blurring is an unfortunate fact of applying a low-pass filter. The low-pass filter what it's trying to do is to reduce the variance of the noise, okay? And so we do that. If we know that if we do an averaging, the variance of the noise will go down by n by n, okay? Now, is also reducing the variance in some sense of the signal, not just the noise. And so when that mask crosses edges, it will blur your edge. Okay, so we're going to see in a few slides that if we use a nonlinear filter, then we prevent blurring. We don't have blurring. Okay, but there is no free lunch in, so there must be some payback for doing a nonlinear filter. Okay, we're going to talk about it. All right. The other thing, of course, we didn't mention that, right? But the bigger it is, I have to do more sums and products. So it's going to take longer to do. So if I'm in a hurry, I have to do a lot of images, then I need to be mindful of that. Okay. All right. So let's try to diminish the effect of this blurring on the edges. Okay? And try to make bigger masks, but that they don't affect so badly my edges, okay? And one solution that you might think of is a weighted average. How does a weighted average help in this sense? Cell phones, please, down. Yes. How a weighted average might help? Yeah, so if I have, I know I have noise, right? So I know somebody added noise to me, and so I ask my neighbors, what do you think I should be? Okay? And now what I'm going to do is I'm going to trust more my nearby neighbors, because they're more like me, and they might have a sense of what I should be. But the farther they live from me, I'm going to trust them less, because maybe they're on the other side of the fence, or the other side of the edge. So what we're going to do is a weighted average where the weights start decreasing, okay, as I go farther away from the center. And you can pick any kind of pattern, but the most commonly used is something that decays sort of exponentially, like a Gaussian, okay? And so the Gaussian filter is one of the most popular filters for noise cleaning, okay? So, here is an example. This is a box filter, and here is another filter. It's not a Gaussian filter, but it's a weighted filter where the center guy has a lot of weight, 4. The 4 neighbors has a little less, 2, and the A neighbor has even less, 1. Okay? And again, all these weights are all positive, and they all sum to 1. Okay? So I have a 1/16 outside, which is the sum of all these numbers. Okay, so this is one example of trying to diminish this effect of crossing boundaries, going too far and mixing things that do not belong together. Okay. As I said, the Gaussian one is one of the most common for doing this type of thing. So instead of having something that decays linearly, it has something that decays like a Gaussian. Okay, don't confuse this with the fact that we're assuming that our model of noise usually is Gaussian. It's not related to that. It's just a way of trying to see how to reduce quickly the importance of the neighbors. Okay. Now, again, I want to ask the question: how big that mask should be? Now that I have a Gaussian filter site, can I make the mask bigger, and how big should it be? Okay. And here it pays. To pay attention to the frequency domain. I know, signal processing is not a prereq of this class, so if you don't understand this, don't worry too much. But one nice thing about the Gaussian filter is that if you look at it in the frequency domain, it also looks like a Gaussian. Okay, so the Fourier transform of a Gaussian is also a Gaussian. What it does do is change the shape, meaning that if I start in the spatial domain or the temporal domain with a fat Gaussian, in the frequency domain I have a narrow Gaussian, and vice versa. Okay, so the standard deviation of the Gaussian is 1 over the other. Okay, but they are both Gaussians. Okay, so now what we're going to do is we're going to try to play a game and figure out how big my filter needs to be. So what I have in the filters actually is a good approximation of a Gaussian. Okay. So one way of answering that question is by looking at the area or volume, if we're talking about 2D, underneath the curve. Okay. Again, Gaussians have distributions, right? PDFs. So if they're properly normalized, the area underneath the curve is equal to 1. Okay? And they have what we call thin tails, right? As I go towards infinity, the curve goes quickly down, right? And so I can figure out how much I need. So this area over here is a high percent of 1. Okay, so here we have the numbers for, if I want that the area underneath is 98.76% of 1, okay, then it means that M, which is the width of my filter, has to be equal to 5, okay, because this is related to sigma, okay, and 5 times sigma, sorry. Okay, so here I have a relationship that if I know how much sigma I want, how big my filter should be according to that sigma. Okay? And we can do the same thing in the frequency domain. We can look at the corresponding Gaussian in the frequency domain and also say, I want it to be basically cover the whole thing here. And that gives me another relationship between 1 over sigma, because this one has 1 over sigma of this, again, times 5, that will give me less or equal than 2 pi, which is a cycle in the frequency domain. Okay? Based on those two things, what that says is that sigma is greater than 796, then M has to be greater or equal than 5, which means is that Gaussian filters tend to be bigger than just box filters. Okay? Box filters are very common to be 3 by 3. But for a Gaussian to really behave like a Gaussian and have the properties of a Gaussian filter, you really want to have something that at least is 5 by 5. Okay? So that's something to have into consideration. So Gaussian filters can be bigger, okay, and they are related to how much the decay you think is going to be. Okay? All right. Now let's switch a little bit and let's talk about implementing these filters. Okay, and so I'm going to mention a couple of things that can be used to speed up the application of the filter to an image. Okay, if you have a very large image, or if you have many images, you want to be able to do filtering quickly. Sometimes what happens is to the same image, you want to apply a set of filters, and maybe you want to be able to reuse some of the computations that you use for one filter when you apply the next. Okay, so those are the things that we're going to talk about. So the first thing I'm going to talk about is that both the box filter and the Gaussian filter, which are the two filters we just talked about, they have a nice property, which means that they are separable. Okay, what means that they are separable is that instead of computing the filtering applying a 2D filter, I can do the same job, exactly the same job. It's not an approximation, it's the same job, by applying 2 filters. Okay, so you say it's more work, but each filter is smaller, so actually it's less number of operations. Okay, so what we're going to do is, instead of convolving with a 2D filter, we first convolve with 1D filter each row, and then we take the output of that and we apply a 1D column filter. Okay, let's see why that might be beneficial in terms of operations. So if I have an image here, and I have a filter that it has k by k elements, okay? Every time I put this filter on top of a pixel on this image, I had to do k-square operations. Do you agree? Right? I had to do the sum of the products of all the elements underneath the mask. So I have k by k, that's k squared. Okay? All right. Now let's say this actually is a separable filter, and so I claim that if I could do it with 2 k filters, k by 1, I have less number of operations, right? So let's look at that. Okay, so I'm dividing my filter into 2 filters. Each of them is k by 1. Now I take my image and I apply one of the filters first. Doesn't really matter which one it is because it's a linear operation, so they're commutative. I can change the order, but let's say I apply the row first. So every time I put this mask on this image, I have to do k operations, right? And then I take the output of that and I apply the other filter now by columns. And again, I have to do k operations, right? So in total, I'm doing k plus k, which is less than k squared, okay? So it's linear in k instead of being quadratic in k, okay? So that saves computation, okay? The Gaussian filter is also separable, okay? So if I can separate this expression as a product of 2 expressions, one on x and one on y. So I can do, again, 2 1D filters and achieve exactly the same response. Okay. All right, so here are examples of filters. This is the box filter. This is the bilinear filter that we saw earlier. And this is a Gaussian filter applied to an image. And here are the corresponding 1D filters, which, again, the rows and the verticals, and in this case, are actually the same one. It's just transpose one of the other. Okay. How do I know a filter is separable? Right. So I can look at it, and by inspection, if I can separate the variables, like in the Gaussian I just did, then I know it's separable. Okay. But in general, I would like to have some way of, that I could program it and tell whether the filter is separable or not. What we're going to do is look at the SVD of a filter. Okay, so again, now we're looking at this image as a matrix. Each element, each pixel is an element on the matrix. We are going to write that matrix as a product of 3 matrices, U, sigma, and B transpose. This is what's called the SVD of the matrix. Sigma is diagonal. U and B have orthogonal columns. Okay, and it looks like this. Okay, and if this is true, right, and we can always find a decomposition like this for any matrix, then it means that F can be written also like this. Okay, you take each column over here and each column over here, and this column gets transposed. So this times this gives you a matrix of the right dimensions, and you scale that matrix by the corresponding singular value, and then you add them out together, you get back the original matrix. Okay? So if, when you do this SVD, you find out that all of these numbers from sigma 2 to sigma k are all equal to 0, it means that I could write my filter as a product of 2 1D filters. Okay, so therefore that would be separable. Okay? If it's not, if these are not zeros, I still can do it as the sum of these separable filters, and there I have to figure out whether it pays off doing that way or doing the k by k filtering. Right? Depends on how many singular values and how big k is. Okay? It's clear? All right. Okay, so here is an example of applying cleaning noise filtering to an image of the space. If you want to count these galaxies, right, you could do a noise cleaning, a blurring. What will happen here now is that the things that were small will get sort of dissolved in the black of space, and only the big chunks will show up as blurry, and then we can do a thresholding. Anything that's brighter than something we are going to do, and this is what you get. Okay? You can play with the numbers of how much blurring and what my threshold is to figure out if this is actually the count that you wanted, or you're still missing some galaxies, or you put some extra that you didn't want. Okay? All right. Okay. Here's an example of applying a noise cleaning to an image that has noise, and as you can see, as I increase the size of the mask, the image becomes blurrier and blurrier and blurrier, right? So how much blur I can cope with depends on the application. In the previous example, I actually wanted the blurring to remove some of the stuff. Okay. Another thing about saving computation is sometimes instead of applying directly a big filter, what I can do is apply a smaller filter multiple times. Okay, so I'm compounding the effect of the filters. So for example, if I have a Gaussian filter with a standard deviation sigma, and I convolve that with itself, that is equivalent to having a filter that has a larger standard deviation. In fact, it's a factor of square root of 2 times the original sigma. Okay, and remember that we saw that the size of the filter depends on sigma, right? So the bigger the sigma, the bigger the filter had to be. So depending again on how big my filter is, it might be more efficient to actually do it multiple times with a smaller filter than just in one shot the big filter. Okay? All right. Now let me talk about something else. Again, for efficiency, in this case, what we want to do is we have an image, perhaps it's a very large image, which we're going to apply to it a lot of box kind of filters, averaging filters, but of different sizes. I want to see what happens when I blur it with a 3x3 and what happens when I blur it with 5x5 and 7x7 and so forth. Okay, because I'm looking at different scales. All right. So the question is, can I do something to save computation? So can I use some of the computations I did for the 3x3 to do it the 5x5 also? Because there is a lot of overlap between this, right? And the answer to that is something very clever, which is called the integral image. Okay? And the integral image is what it does is, given an image, we're going to sum increasingly larger sub-images of that image. Okay? Let me show you with an example so it's easier to understand. Okay? So this is the equation. What it says is that F is the name of my image. KL are indices that move me along the image. And what I'm going to do is create a new image that I'm going to call S, that at location ij will have the sum of the upper left pixels in my image up to ij. Okay? Clear? Let's have this image over here. Okay, this is the original image. And eventually I want to do, for example, an average on this green area. But for now, don't pay attention to the color. Okay? What I'm going to do is from this image, this is F, I'm going to compute S. Okay? So S is given here. And see, for example, the first pixel is 3. But this guy is 5 because he has 3 plus 2. And this guy is 12 because he has 3 plus 2 plus 7. Okay? This guy has 4 because he has 3 plus 1. And this guy has 11 because he has 3 plus 2 is 5, plus 5 is 10, plus 1 is 11. So it has the sum of these 4. You get it? Okay? So I'm always adding up the upper top left region of my image. Okay? Now, how does that help? Well, first of all, I can compute this image efficiently by using the previous sums up to that point. right? Let's say I have completed the first 2 rows and half of the 3rd row, and I want to figure out what to put here, okay? This 28. Again, I could do this first row, plus this 2nd row, plus these 3 guys, and that is 28, right? But that's not how I want to do it. How can I do it more efficiently? How can I use what I already had computed? So this guy, sorry, is the sum not of the is the sum of these 3 by 3 neighborhood, right? That's the 28. So how do I get that 28? Yes.
I mean, the last entry in the row is what the sum of everything, or is the
So 17 is the sum of these 6 numbers over here. Okay. And again, what I want here is the sum of these 6 numbers plus these 3 numbers. So I'm missing this last column, right? How can I? So yes, this guy is going to be 17 plus something, right? And that plus is equal to 7, 1, and 3. So I had to add to that 11, okay? Which 17 plus 11 gives me 28. But can I do even more? So you're using this 17. Can I use more of what I already have pre-processed to speed up?
17 plus 19 minus 11.
Right. So if I add 19, 19 is adding these 6 guys, which is adding the 2 that I needed, these 2 that I needed, but it's also adding these 4 that I already had, right? So I need to take them away, right? And how do I take them away? Because this 11 is the sum of these 4, okay? So I add 17, I add 19, subtract 11. Am I done? No, what I need? I need to add a 3, right? So I'm doing this portion, I'm discounting 1 because this I counted twice, and then add this guy. Right? And as I go farther and farther down my thing, that becomes even more beneficial, right? So here it might not look like much, but as the image becomes very big, I'm saving a lot of computation by doing that. Okay? So this is what's called the integral image. Okay? Now, it's a cute thing, but so far I haven't shown you how to use this for filtering, right? How do I do filtering? Well, suppose I want, again, to apply a 3 by 3 filtering over here, right? So what I need is the sum of all these numbers in green and divide them by 9, okay? Now, how do I get this thing? Well, same trick as before, right? What I will be doing is using partial sums and subtracting when I have more than one thing counted twice, okay? So I look at this whole thing, that's 48. That gives me the sum of the 4 by 4, which is part of what I want, but it has more stuff that I want. So then I need to take away this thing, which is given by 13, okay? I need to take away this thing, which is given by 14, but I have to be careful that this guy now is being counted twice, okay? And then I have what I need, okay? So 48 minus 14 minus 13 plus 3, that will give me the sum of the green numbers, okay? And the thing is that I can use that, I did it here with 3 by 3, but if it was 7 by 7, I still do the same thing. I need to look at the corner and do this game, and then just divide by the number of things. Okay, so I pay up front by computing my integral image, although we saw that we can actually reuse some of the stuff as I computed, and then I have almost free solutions with filters on any side. Good. All right. So all of this was nice. We saw that averaging reduced the variance of the noise, okay? But it's a low-pass filter. So what this means is that what it's doing is attenuating high frequencies. The idea was here that the noise probably was high frequency, and so I wanted to get rid of it. But my edges are also high frequency, so I'm blurring my image. Okay, so I'm also attenuating the high frequencies of the signal. Okay, so that's not so good. Okay, we saw that 99 in my example, that's what's called impulsive noise. It was not very good at removing it because, in fact, what it did, it was spread it. It brought it a little down, but then spread it all around. Okay. So what we're going to look as a solution for that is nonlinear filtering. Okay, and I think I already gave it away. The way we're going to do this is with a median filter. Okay, so the averaging filter is computing the mean of the neighborhood. Okay, now what we're going to do is replace mean by median. Okay, what's the difference between mean and median? What's the mean and what's the median of if I give you a list of numbers and I ask you what's, like, you know, I give you the grades of the exam, right? And I say the mean in the class was this and the median was that. What does that mean? How do I compute the mean?
The mean is adding up all the values and dividing by the number of them. Median is finding the center value.
Right. I need to sort, and that's the no free lunch, right? Because sorting is expensive. Okay. I need to sort, and I pick the middle guy. Okay. And why that might be advantage?
Because if you're on like an edge of like black and white, you have a bunch of white on one side and one black value, you'll just pick a white value and not average.
Yeah, you will not be mixing things. You pick one or the other. Yeah. So that is not blurring. And what about my impulse noise, my 99? It's in the tail, either in the beginning of the list if it's very small, or in the other end, if it's very high, it will never end up in the center. So those guys disappear effortlessly. Okay, well, not effortlessly. I have to sort. Okay, but that's the idea. Okay. So this is again the example before. Again, if you sort things here and you pick the middle guy, this ends up being 10. If I have over here, which is what's one of the boundaries, again, I end up picking 10. Over here, that this was a guy that there was 99, the 99 ends in the end, so this becomes 10, and so forth. Okay, so the bad thing about this filter is that nonlinear. Okay, and why is bad being nonlinear?
You can't represent it with matrices.
Right, that's one thing. Another thing that might... The order matters. Okay, so I had to be careful how I apply my filter. It's not so easy to combine filters together into a big filter that's the whole job in one shot. Okay, and in this case, it's also more expensive to compute because I have to sort the numbers. Okay, so the good thing though is that it doesn't spread the noise. It can remove spikes, and but the downside is expensive to run. So here is an example of a very noisy image, where, by the way, the noise it's noise that's actually very good for the median filter, but not so good for the average filter. So what it has is a sort of noise that we call salt and pepper. Okay, so you add every pixel randomly. You select whether you wanted to change it or not, and you change it all the way either to white, that's salt, or all the way to black, that's pepper. Okay, so randomly select how many pixels you want. And here it's a large amount, a large proportion of them have been switched. Okay, and I want to clean them up. Now, if I do an averaging filter, what happens is that this salt and pepper becomes actually bigger grains of salt and pepper. Okay, they get blurry. You might say that this is better than this, but really it's not a very good output, right? If you apply a median filter, you get something like this, which is almost perfect. Where it's not perfect? there are some gaps in the black stuff here. For example, it depends whether I was unlucky and my noise fell off right at the place where it could be confused with my neighbors because I have more of the other neighbor. Okay, so if my noise was similar to the signal in the neighborhood, then I could be. Also, if I happen over here, these are not truly uniformly distributed, but if I have a clump of a lot of pepper together, right? When I sort a lot of pepper, I will get pepper. Okay. All right. Okay. That's it for noise cleaning. Any questions? Yes.
With the non-linear filtering, do you lose like data when you do that, or is that doesn't really matter?
Do I lose data?
Well, because you're like choosing one or the other, but you're not doing the average, so.
Well, but I'm hoping I'm choosing the right one, right?
Okay.
So when I do the average, I am inventing something that was not there in some sense. I took a little bit of this, a little bit of that, and averaged them, and I got. So, yeah. Yeah, if I had the crystal ball and I knew exactly what the noise was, I could go and remove it. But the problem is random, and this is the best I can do with these tools. All right. Okay. All right. So let's move on and let's talk more a little bit about linear filtering. But now instead of doing noise cleaning, what I'm interested in is in finding boundaries, finding edges. Okay. And edges are very important features. If I give you a line drawing or something, right, just a sketch, you probably, not if I draw it because I'm not that good at drawing, but if an artist did that, you're probably pretty good at knowing what that was about. Okay, so edges themselves carry a lot of information which are useful for doing detection, recognition, and so forth. So let's talk about how we find them in images. Okay. And that's one feature. In this class, we're going to talk about more features. So here I have a sample of images, right? And one feature, as I said, is edges. And this is that. And you can see that in some cases, edges are helpful, but in others might not be so much, right? So if I gave you these pictures to begin with, I didn't show the images where they came from. You still can tell exactly what these guys are, right? This is a traffic sign. This is an old car in a park, and this is a little kid. But this might be harder to figure out what it was, right? Well, it was a field of beautiful tulips in bloom. On the other hand, if I knew that was about, looking at these edges might help me try to understand the density of how many flowers I had in the garden, in the farm. So edges are not totally useless here, but what I'm saying is that in terms of semantic meaning, that when we look at these edges, this one meaning less to us than this one. Okay, so for that reason alone, we are going to be looking in this class to more features than just edges. Edges is just one feature that helps us trying to understand things, like for example here recognizing letters, so we can understand what this sign is saying, or knowing what kind of art is this. Okay. Sometimes we'll be thinking in terms of texture, so I have regions that can be separated. And sometimes it's easy to go back and forth between edges and regions. Like if I have a region and I follow the boundary of the region, I have an edge. Or if I have the edge and I close the contour, I have a region inside. Okay. Now, unfortunately, life is not that easy. Okay. And what we're going to see is that it's not as simple to go back and forth between them, because detections are imperfect and segmentations also are imperfect. So over here, for example, we get the hair of the kid split into two regions that probably I didn't want to. Okay. Over here, the letters are fairly well done, but still the W's look terrible. Okay. Over here, the colors of the tulips had been separated more or less okay, except for this band over here that was kept as a single band. Okay. So a practical definition of what image features are some local features. They're local things that are extracted, local information extracted from the images, and that hopefully are useful for our application. Okay, and so they have to be local, they have to be meaningful, they have to be detectable. I have an algorithm that can extract that from the images. Okay. Now, as I promised, I'm going to talk about edges today. And this is actually related to the first project, which I haven't discussed yet. Okay. So let's see. I have here a sketch of an object, okay, in the world. It's like a bottle, has some sign, letters on the surface. There's a shadow on the table that this bottle is landing. And you know, this, again, is an edge drawing of what is seen. And as I said before, you know, based on this edge, we can understand what's going on, right? And we know it's a bottle that has these letters on top of it, and there's a shadow. Okay, now all these edges did not come to be for the same reason. They have different physical explanation. Okay, so the edge here between the top of the bottle on the side of the top, right? Came because there is a surface discontinuity. The normal of these two surfaces are different. And therefore, I see that edge over there. Okay? The edge here along the side of the bottle, we know that that's not a truly an edge, right? What we're seeing is a cylindrical bottle. And what we're seeing is basically where our line of sight is tangent to the surface of the object. Right? So I see a line there, but really there is no line, right? It's a surface, and I'm seeing that. So over here, what we have is a depth discontinuity. I'm seeing the edge because I'm seeing the foreground, the bottle, against some white background. Okay. These edges over here, they are neither of that kind. They came about because somebody painted these letters on the surface. Okay. So they have different color, but they don't have different normals. Well, they have different normals over here because I am on a cylinder. But if it was painted on a flat table, I would still see those edges, and there was no difference in the normal. Okay, and these edges over here came because I have some illumination discontinuity, right? There's a shadow being cast from the light source. And so, again, I have multiple edges, and they all came from different reasons. Okay? Nevertheless, what we're going to see next is something that's going to just to find edges, regardless of how these edges came about. Okay? Next class, we're going to think about edges in terms of more semantic way, and so perhaps I'm not interested in that case in the shadow. I'm more interested on the shape of the bottle. Okay? But for now, because we're going to look things at a very local way, I don't really care how these edges came about, but I'm going to detect them in the image anyway. Okay? So here's an example again. Instead of having that line drawing, this is in a real picture, right? And again, I have shadows, I have boundaries, I have changes of surfaces, etc. Okay? So if you look at those places in the image, and here I have a blow up of things that you see that here in the sky, well, the patch looks basically constant. Okay. Again, if I blew up, I would see the noise in it, and it will not be fairly as constant. But in general, there is no edge around here. If I took a region around here on the boundary of this tower, and I blow up here, what you see is this line, right? Because I have this surface of one color, and then the sky behind of a different color. So this is again a depth discontinuity, but I see this as a change in grayscale values, in this case going from dark to brighter. Okay? And if I look over here at this piece of the fountain, well, I see this more complicated thing, but again, what you see is that edges can be observed by looking at abrupt changes of grayscale color. Okay? So that would be the motivation of how to design a detector to find these edges. Okay? Because images are 2D, we can think of the grade level values as a surface. I have done before that the same thing with the cameraman picture. And so here what you see is the 3D representation of this 2D image. And again, edges will look like cliffs in this 3D surface. Okay? So what we need to do is find a way of detecting those things. That's the task. Okay? All right. So we're going to start simple. Let's think of an edge like this, where I have this is vertical edge, and half of my image is dark, and the other half is bright. And for now, I'm going to consider just edges along one direction of my image. Okay, so what I'm going to do is I'm going to look at one row of this image, indexed by column. So here I have the axis that measures, the columns on this image. And really what I'm trying to find out is this abrupt change that went from dark to bright. Okay? So I really want to find this location, which is the location of the edge. All right? Now, this is a cartoon of how the 3D surface will look like along this row. Right? So what I did is I'm plotting along the column the grayscale value, and this region is dark. Dark means low. This region is bright. That means high, right? So what I draw sort of something is a thing that starts low and goes high, okay? And I didn't do it in a very sharp vertical cliff because real images don't happen to be like that. Real images are already a little blur, okay? So I have like a transition from here to there, okay? So again, what I want to do is to find this change. What mathematical tool is the most natural thing to apply here to find this change?
Derivative?
The gradient, right? The derivative, okay? So what I'm going to do is take the derivative of this function, okay? What does the derivative tell me? What happens to the derivative around here? Very low, right? Why?
Because there's no change.
Because it's not change, it's fairly constant. Same thing here, right? But over here, there's change, so the derivative should be high. Okay? So this is the plot of my derivative of this cartoon, right? I start fairly low, then I start increasing, and then I start decreasing. Because again, I have this smooth kind of thing that I did in my profile. Okay? So I start going up, and again, I'm getting steeper and steeper, and then I start flattening out, so my slope, my derivative goes down, and then goes back again to fairly low. Okay, so now finding the edge can be translated to looking at this plot and find out where the peak is. Right? So I take the derivative, I look for a peak. Where I have a peak, I say I have an edge. Okay? Okay. Now, that was in the continuous domain. That was a cartoon. Let's go back to discrete. Okay? So, in discrete, what we're going to use is, instead of derivatives, we're going to use differences. Okay? And here what I have is the mathematical definition of the derivative, right? If you remember, it's a limit between the ratio of the function plus an incremental movement of the variable minus the function before the movement divided by how much I move, and then I make the movement go to 0. So that will give me the tangent. Okay? Now, in discrete, what we're going to do is replace the tangent of the curve by a chord. Okay? So what we're going to have is the difference of the function at 2 points. Okay? And what I'm going to do is, instead of doing f of x plus delta minus f of x, I'm really doing f of x plus delta and f of x minus delta. So I have my difference at the center. Okay? So now I have f of x plus 1 minus f of x minus 1, and now the delta is 2, so I will be dividing by 2. Okay? So I'm approximating the tangent by this chord. Okay? I move 1 to the left, 1 to the right, do the difference, and divide by 2. Okay? All right. So that means that I can use a mask to find edges, right? And the mask, what it needs to do is this difference. Okay, so I have 0 in the center, and then I have -1 and +1. And then to be consistent with this, I will have to have a 1/2 outside, okay? Which right now I'm going to forget about it, because really what I'm looking at is for, is there a significant difference there? I don't care too much about the scaling factor, okay? All right? Okay. So we thought we had solved it, right? So let's go and try it, okay? So I have this image that has the look of what I did in my cartoon. Half black, half white, a blurry edge in the middle, but this image is noisy, okay? And so when I plot one row of this image, this is what I get, okay? So a lot of bumps over here, but low, a lot of bumps over here, and then, you know, a fairly steep change between there. It's not vertical, but it's fairly steep, okay? Now, when I do the derivative of this, I get something that looks like that. Where is my head? It's hard to know now, right? The derivatives are bad for noise, okay? We saw that when we average, we decrease the variance of the noise. When we do differences, we increase the variance of the noise, okay? What would be the solution to this problem? What I would threshold here?
Not there. First,
Here?
maybe.
But that, still we have to find, after I threshold, we have to find the edge.
Filter it?
Hmm?
Filter it?
Filter it, how? What would I do?
Non-linear.
Low. I would do a cleaning of my noise, right? So I'm seeing noises. Average so that I remove the noise and then work on the clean image, okay? But let's first check about what I was saying about that taking differences actually increases your variance, okay? So we're going to do exactly the same thing as we did before for averaging, right? So I have my additive noise model. I am assuming now that my noise is zero mean and a standard deviation sigma, and it's uncorrelated. Here I'm saying it's Gaussian, but really Gaussian doesn't matter as long as uncorrelated zero mean standard deviation sigma is the same, okay? And now let's take differences, okay? So I have I of x plus 1 minus I of x minus 1. And when I take the difference, I group together the ideal terms. That would be my ideal gradient, right? That's the difference that I wanted. But then I have this thing over here, which is the difference of the noises. Okay? And so the output noise, the expected of the output noise is still 0, right? Because it's 0 plus minus 0 is still 0. But the variance, what happens is I have the variance of n squared of x plus 1, n squared x minus 1, and then 2 times the cross product. The 2 cross product goes away because they are independent. But I still have these guys. And what happened was that this minus that was here got not converted into a plus. And so now I have actually twice the variances before. Okay. Now, there's only, I'm a little bit disingenuous here because in the previous slide I said I'm throwing away the 2. If I divide it by 2, I will get back to where I was, right? So if I keep track of my scaling, it's not as bad. But still it's bad, okay? So what we're going to do is clean and then do edge detection, okay? And here's where it pays to use a linear noise cleaning, right? Because if this is linear and this is also linear, the combination is also linear. And so instead of having to apply 2 filters, one after the other, what I can do is design a filter that does both jobs at the same time. Okay? Here is how we do it. Okay, so again, this is the noisy signal. Let's say I apply a Gaussian averaging filter to this. that will clean the noise, okay, by smoothing it out. It will also smooth somewhat my transition, right? Here was sharper than here, right? But not too much. Why? Because this is a Gaussian filter, okay? So the Gaussian filter has less weight as I go further away, so that means that a little better preserved than if I did a box filter, okay? And so now that I have this, now I do the for the derivative of that, and I have now this nice peak that I can threshold and find out where my... Here I did it one at a time. I did the filtering first, and then the noise cleaning first, and then the edge detection layer. But what we can do is use again what I said, that these two filters are both linear. I can combine them together into one. Okay, so here what it says is that if I have the convolution or correlation between two filters, H and F, okay, and I take the derivative of that, that's the same as taking the derivative of one of the terms and then convolving, or taking the derivative of the other one and convolving, okay? So I can choose. So instead of applying two filters, what I can do is apply one filter, and the filter would be the derivative of the Gaussian, right? So the Gaussian was the cleaning noise. The derivative, that's the edge. Combine those two together, and so now I have a filter that looks like this, okay? And it's very intuitive what is happening, right? So it's still doing the difference. I have a positive lobe and a negative lobe here. But at the same time, it's doing the averaging with this Gaussian, okay? So I will get exactly the same solution as if I did it one step at a time, okay? Now, this is in 1D. I can do the same thing in 2D. So if I have an image that has now an edge that's not along a row or a column, right? What I need to do is, instead of taking derivatives, what I need to do is take the gradient, okay? What that means is I need to take the derivative with respect to one axis and the derivative with the other axis. That gives me two components, okay? That's the gradient vector. And that gradient is perpendicular to the edge, okay? Now, how do I know that I have an edge? When I have 1D, I was doing a thresholding on the derivative, right? How do I threshold a vector? It's kind of not nice to do, right? So what do you do?
Average or sum of them?
Yeah, I could do that. Basically, what I do is that I take the norm. It could be the norm 1, what you're saying, or I can have the norm 2. Okay, but it's basically take the amount of jump in the direction of the gradient and threshold that. Okay, so this is the two norm. You were talking about the one norm. Either one is fine. Okay, and I can also find the orientation of the edge, right? And the edge, again, is perpendicular to the gradient vector. Okay, so if I know the orientation of the gradient vector, then I know the orientation of the edge, which is rotated 90 degrees. Okay. Okay, so if vertical edges were found with a mass like this, horizontal edges are found with a mass like that, right? And any edge can be found with a combination of the two. This one is finding the partial derivative with respect to one dimension. This is finding the partial derivative with respect to the other dimension. Okay. Now again, this is not careful with the noise, right? If I want to be careful with the noise, I need to do some noise cleaning. I mentioned in the previous example a Gaussian filter. We're going to see next class that actually the Canny edge detector does exactly what it does. But before Canny came, other people did simpler edge detectors that had this kind of shape, right? So instead of having just one row of this, I repeat now 3 rows, okay? And what is the physical meaning of what is happening? What is this filter doing? Well, it's doing differences along this direction, but along this direction it's doing averages. Okay, it's the convolution of a vertical filter with ones and the horizontal filter that has -1, 0, and 1. So it's doing a smoothing with a box filter and differencing at the same time. Okay, this filter has called the P-width filter, okay? And this is for the vertical, and there is similar one for the horizontal. Okay, and again, these are the pre-width. Now, variations of the pre-width filters give more importance to my 4 neighbors versus my A neighbors. Okay, so instead of having here a -1 and a 1, what you have is a -2 and 2 at the center. Okay, so these are another set of filters, and these have also a name. They're called the Sobel filters. Okay. Okay, so here's an example before we leave of finding edges. This is a very clean image. It has zeros over here, and then this quarter over here is all 50s. I would like to find the boundaries between the zeros and 50s, right? So I'm going to do apply the gradient masks. So this is in one direction. This is finding horizontal lines. And if I run this mask along this, assuming that this image is infinite, it keeps going 50, 50s, and 0, 0s all around, this is what I get. Okay, so around here, I get this 250s, and then I have 100s, and then it goes to 150s. If I apply the other mask, looking for vertical edges, this is what I get. Okay, so this is the first component of the gradient, and this is the second component of the gradient. So at every pixel, I have defined a gradient vector. Each gradient vector has 2 components, and each represents a separate image. Now I ask you, where is an edge in this image? And so what I need to do is look at the magnitude of the gradient at every pixel. Okay, so what do I need to do is take this guy and compare and square it up. Sum with the square of this guy, take the square root, and then say, is that high enough? Okay, or I could do like he said, just do the sum of the absolute values. Okay, so here's my gradient. Okay, here's the magnitude of the gradient, and now I have to pick a threshold, right? So if I pick a threshold that's, say, greater than 50, right, I will pick these pink numbers as where my edge is. Okay. Now, one thing that you should notice is that I'm not finding a single line boundary. My boundary is 2 pixels thick. And that's a result of having a 3 by 3 mask. Okay? Questions? No? Okay. So let's stop here. As for the project, I want you to start thinking this weekend, how is that what I just covered, edge detection, can be applied to find motion detection in a video. Okay, that's what the project is. So the project is, I have already given to you in Blackboard a bunch of videos. Okay, they were captured with a stationary camera, but there are things that are moving in front of the camera. And I want you to detect what is moving, okay? And if you read the project assignment, I'm walking you through it, okay, that we can apply all of these ideas to that problem. So we can morph the problem in a way that instead of thinking in terms of space, now we're thinking in terms of time, okay? So we'll talk more about that on Tuesday after the weekend, okay? Have a good one.